I'm Lorenzo Bianchi. I'll be here for a couple of weeks, and it's a great honor to be opening this very nice program. So let me start by thanking the organizers. Two of them are here. Others are probably following remotely, but for putting this program together on this topic, which is particularly interesting for me, that is boundaries and defects in quantum field theory. My talk will be based about work in progress on analytic bootstrap for holographic surface defects in collaboration with Davide Bonomi, Maddalena Ferragatta. Davide is a postdoc, Maddalena is a student in Paris, and Valentina Forini, who is also one of the organizers of the program. The techniques that I'll be spending most of the talk explaining are actually better described in earlier papers in collaboration with Davide Bonomi, Elia de Sabata, and Aleix Jimenez Grau. So the idea, I don't think I need to give a lot of motivation, since we have a 3-month program on boundaries and defects. So I guess we all think that defects are important observables in quantum field theory. But let me write it anyways. It's the first talk of the program. We have many different examples of defects. Most famously, maybe Wilson lines, Stoff lines, boundaries, but also the defects that we are going to be talking about in the second part of this talk are surface defects, in particular Gukov-Witten defects in unequal force superior meal. Surface defects are also important observables because they somehow they probe some phases of the theory that are not accessible to other observables, in particular to local operators and line operators. And what we care about is that they are also important in holography. And holographically, usually defect, well, they can have different realizations, okay? But they usually, most of the realizations that we know explicitly, especially in top-down examples. So when you look at type 2b supergravity, or when you look at probe brains in ADS 5 versus 5, you find that the defects that we normally study in the gauge theory corresponds to brains, or in the case of the Wilson line, also fundamental strings in ADS 5 versus 5. So let me briefly outline what is going to be the plan of my talk. The idea here, okay, let me outline the main idea, which is the main take-home message of the talk, is that we can, is an idea that is somehow borrowed by what people did in the homogeneous examples. So the idea is that you can study holography without doing holography, essentially. So we're not going to be using much of supergravity. If I have time, I'm going to tell you what is the computation that we should do in supergravity or in holography to actually compute the observable that I'm going to introduce, that is a 2-point function of operators with a defect. But we're not going to use holography to do this computation. We're going to use analytic bootstrap. Okay, this is something that people have done also with 4-point functions in ADS 5 versus 5. They use analytic bootstrap, so they essentially use consistency conditions and crossing equations, unitarity, and all the constraints that we know on the spectrum of holographic theories to extract information about correlators without actually doing Witten diagrams, essentially. So first of all, the plan of the talk is the following. First, I will introduce the observable. The observables that we're going to study is a 2-point function of one particular supersymmetric chiral primary operator, that is the 20 prime operator in n equal 4 superior meals, in the presence of defects. Okay, but the general setting is valid for any scalar operator. Well, we do it for scalar operator, but in general it can be applied to any operator that you want to insert in a given theory under some circumstances, under some conditions that I will explain in details during the talk. Then I will introduce the main tool for this derivation, that is a dispersion relation for this observable. So what is a dispersion relation? Is essentially an integral equation that reconstructs the full correlator, these 2-point functions, starting from a discontinuity. Okay, and then I will outline some applications. Well, I won't actually outline much. I will list some applications. So I will list some of the contexts where this dispersion relation and analytic bootstrap techniques have been applied in the constants of defect. And then I will discuss the main application, that is the new one, the one we are developing with Davide, Maddalena, and Valentina, that is surface defects. Well, we'll see how we go with time, actually. And of course, we'll have then some conclusion and outlook on what we are still missing. Let me see how to use these blackboards now. This should be OK. Yeah. So giving the first talk of the program is nice because you open the program. It's a great honor, but it's also the one where you need to do the whole introduction on defects. So let me do it. I'll start telling you what we mean by a conformal defect. Well, maybe I don't need to, but I think it's important to be all on the same page. So what is a super conformal defect? Well, let me start by a conformal defect, and I will also introduce supersymmetry later in the talk. So if I start with a conformal field theory, which is which has let me take it to be in Euclidean. So it has a conformal group that is SO1, D plus 1, and then I break it to some defect. Let me pick also color for a defect. Red. The defect is breaking the conformal group down to P plus 1 times. This is all something that you all know, but it's just to set the notation. So I have the conformal group in P dimensions. This defect lives in P dimensions on a flat or spherical submanifold, and SOQ is the orthogonal rotations. So I have rotations in Q dimensions that are orthogonal to the defect. This is okay. This is an additional requirement. We will see that actually in the main example of my talk, so surface defects in n equal 4 superior meals, this orthogonal rotation is not preserved. Okay, so this is not necessary. You can see that in some explicit realization of superconformal defects, it's not just, especially in particular when Q is equal to, so when you have codimension 2 defects, you can preserve a combination of R symmetry and orthogonal rotation and not the full group of orthogonal rotations, which makes a big difference from what I'm doing. And the reason why the paper is not out yet is precisely because there is this breaking of orthogonal rotation, which makes things a little bit more difficult. But I will discuss this toward the end of my talk. So what do we have when you have a defect? When you have a defect, you have non-trivial 1-point functions, and you have non-trivial bulk to defect 2-point functions. So let me. These are the two main observables that are completely fixed by conformal invariance. So if you have an operator here, another operator here, and a defect operator which I will denote by O hat. Well, just to introduce the notation, again, you probably know when I mean by a one-point function in the presence of a defect, I will probably forget about this D in the rest of the talk, but all the correlators in these talks are going to be with the defect. I mean that I take the correlator of the operator with the defect and I normalize by the defect expectation value. And this is fixed by conformal invariance when you have a conformal defect to be something like, can I invert this maybe? Let me see. This is fixed to something that I call AO divided by the distance x orthogonal to the dimension of the operator O. And the distance x orthogonal is actually the only non-vanishing distance that you have in your problem. And here you have a similar thing. So also this object is completely fixed by conformal invariance. This is what you call a bulk to defect coupling. And we call it, we normally call it B-O-O hat. And OK, there is some kinematics that is, again, just conformal invariance. If you want, I can write it down. But it's just some orthogonal distance to the delta. It's easy to work out, especially if you work in, let me put this in x and this in y. OK, so the other important object so these are called bulk to defect couplings. The reason why these are called bulk to defect couplings is that is because you have a new OPE channel that is essentially the defect OPE. So you take an operator in the bulk O, you bring it closer to the defect, and you can write the operator O that sits in the bulk as an infinite sum of local operators living on the defect. And these couplings that you have in this OPE, if the operators, if the defect operators and the bulk operator are unit normalized, they are precisely the bulk defect couplings that you see there, essentially in the same way like the 3-point functions appear in the OPE of two local operators in an ordinary CFT. So you sum over O hat, and then you have some coefficient here will depend on the orthogonal distance and parallel derivatives acting, some differential operator acting on O of x parallel. Yeah. This one is a definition of conformal defect. So yes, I would say you can say that certainly if you have all these properties that are realized, then this is a good conformal defect. I think. It's a necessary and sufficient. Let me think. Well, I would say so, but yeah, if someone, I can be wrong on this. I would say it's also sufficient condition having these conditions here. Certainly, what I can say is that these data here, they are known as defect CFT data, and so once you know well, you know, when you have an ordinary homogeneous CFT, you need to know the dimension, the spectrum of the theory, and the 3-point functions, and you completely solve the theory, right? Because through the OPE, you can actually compute all your correlators. Okay, so these now introduce these objects that I introduce now. They are a new set of defect CFT data, what we call the defect CFT data. So once you know the one-point functions and the bulk-to-defect couplings, you have completely solved the theory. Well, I should say also that this spectrum, so you have new operators on the defect. So the operators on the defect, they have new dimensions, new 3-point couplings. So this is on the defect. This is as much as an ordinary CFT, with the only difference of this that this CFT is non-local. Okay, so there is no stress tensor that is localized on the defect, but you have an OPE between among operators on the defect. You have the dimension, the spectrum of operators on the defect. So you have a standalone CFT on the defect that you need to solve. So if you know all the spectrum of and 3-point couplings of operators on the defect, and you also know one-point functions and bulk-to-defect coupling, you certainly solved the defect CFT. Now, what you may ask is, okay, but do I really need to know all of this data to actually solve the DCFT? This is a question that is a bit subtle, but I can immediately tell you that there are non-trivial relations between these defect CFT data through what is called the crossing equation. And now I'll introduce the crossing equation. If I can find an eraser. This eraser is on the table here. Ah, yeah. There's a choice. This? Yeah, try this. So the crossing equation is an equation as much as in the homogeneous CFT, which relates different channels, different OPE channels. But now it's a bit different, because in defects, the crossing equation relates to channels that are qualitatively different. And I'll show you why. First of all, I need to introduce the observable. So the main observable of the talk is the 2-point function in the presence of a defect. So what you have a defect, but now you have 2-point functions, and both these operators are in the bulk. Okay, so you have OX, OY. And this function now is not fixed by conformal invariance as much as the 4-point function in homogeneous CFTs. So this function now is, well, you can write down a prefactor which accounts for the conformal dimensions, the scaling dimensions of the operators, but then you can build cross ratios, and this is the main difference. So here you can have a function of 2 cross ratios that I'm calling Z and Z bar. This is for brevity. Actually, there are different set of cross ratios that you can choose. Z and Z bar are maybe not the most immediate one that you can pick, but they have a nice geometrical interpretation as much as in the 4-point function. You see the structure of this object is very much similar to the 4-point function in homogeneous CFT, where you have also 2 cross ratios that you normally call U and V, and then you have Z and Z bar that are related to U and V. In this case, I don't introduce the cross ratios that are normally called psi and cos phi, that are the usual, because it's easier to work in terms of Z and Z bar if you think that you use conformal transformation to map your situation, to map your 2-point functions to a particular conformal frame that will find very useful in the following. So let's think now in Euclidean for a second, and let's go to this conformal frame where these Z and Z bar have a nice geometrical interpretation. So imagine you can use all conformal transformations to actually fix as much as you can in this 2-point function. Okay, so first of all, you have the defect. Let me take a perspective now where the defect is in p directions that are orthogonal to the plane of the blackboard, and then you can actually show and now you have a set of conformal transformations that you can use that are the ones that are actually preserved by this defect. So the conformal transformation that you can use is essentially SO1, P plus 1, okay? And orthogonal rotation. So first of all, you use the preserved conformal transformation to set both your operators on a single plane orthogonal to the defect. This may be not that completely obvious, but you can do it. I can tell you can do it. Well, there is the non-obvious thing is that there is a specific special conformal transformation, which once you choose the plane of one of the 2 operators, move the other operators on the same plane. This is you can do it. You have to trust me. And then you use dilatation to put dilatation and orthogonal rotation to actually put one of the two operators in point 1, and then the other operator is essentially on point O of x, y, where x, y are essentially, so the defect, now we take it to be the origin. This is just choice, translation invariance. And it, of course, it identifies, the defect identifies 2 points because it identifies the origin and infinity, because the defect is present also at infinity. And now you have the point 1 and the point x, y, and the z and z bar in this particular conformal frame where you have fixed all your points, then it's simply, these are simply complex coordinates. In Euclidean, these are simply complex coordinates in this plane. Okay, so this is why am I saying this? Because the full techniques is based on the analytic structure of that function f on in the complex plane of in the two complex variables z and z bar. So I really need to be sure that you understand very well what is the physical meaning, the geometrical meaning of this z and z bar. So now, what I was saying is that you have a crossing equation. What is a crossing equation? Well, this 2-point function, you can expand it into different channels. Okay, so you have what you can do, as much as you do in homogeneous CFT, you take first the OPE of the two bulk operators. This is an ordinary operator product expansion of two operators in a CFT. Okay, so you take these two operators and you write it down as a sum of infinitely many bulk operators that are then exchanged with the defect, in the sense that you can compute here. You have some delta and L. So, and here what this picture means is that you have a sum over delta L of essentially the 3-point couplings of O, let me call O tilde, the operator that is exchanged here in this OPE channel, times a 1-point function of this operator O tilde. What you're doing, you're taking a 3-point function because you're taking the OP of two operators with this operator O tilde, and then this operator O tilde is left alone in the correlator, so it's a 1-point function of this operator O tilde, times some functions, f delta L of z and z bar. What is this function? This function is called a bulk conformal block, is essentially resumming all the, so here you are summing over delta and L of all the primary operators that are exchanged in the bulk. Okay, so you know that you have conformal field theory, you classify operator in primary and descendants, and the idea is that these conformal blocks given a certain dimension and spin of the exchanged operator in this channel, is essentially resumming the contribution of all the descendants. Okay? This function here, the important thing about this function is that it, well, if you really are computing the 2-point function, you also want the prefactor, right? So what I should say is that this is just a function f of z and z bar that you can write like this. You always have that prefactor in front, okay? So the important thing is that this function here is completely fixed by conformal invariance. It may or may not be an explicit function of z and z bar, but it is certainly fixed by conformal invariance, in the sense that you can write it down. Well, there are different ways of obtaining this, but one way is to write it down as a solution of some differential equation. You may or may not be able to solve the differential equation explicitly, but it certainly tells you that this is a known function. This is a fixed function, and you can easily expand it as in any as many orders as you want in Z, as a series expansion in Z and Z bar. And then you have a different OPE channel, and the different OPE channel is when you take both operators O and you bring them close, you bring them close to the defect. Okay, so in this case, you're doing something different. You're taking both operators and you're taking an OPE expansion with a defect. Okay, so that means you are essentially taking, again, this is referred to the function f of z and z bar. you're taking an expansion, and now what are the coefficients that enter here? These are essentially anytime I have it somewhere hidden below this blackboard. Whenever you take a de facto PE expansion, you pick a B factor. Okay, so essentially what you're doing here, you're summing over the spectrum of this operator that are exchanged on the defect, which we normally put here with the O hat, delta hat, and S. I'll tell you what S is in a second. And then what you have is a square of this B, okay, and some functions of Z and Z bar that are completely fixed by conformal invariance, and these are the defect blocks. It turns out the defect blocks are actually easy to solve in any dimension. So these are actually known functions, product of hypergeometric functions, essentially. It's a product of two hypergeometric functions in any dimension of defect and bulk. Okay, so what is delta hat? Delta hat is the dimension of the primary operator. Again, these operators on the defect are classified in primary and descendants, where descendants are derivatives just in the parallel directions. So these are the dimension of the primary, and this S is the spin. Actually, a generic operator on the defect will have parallel spin and orthogonal spin. This is just the orthogonal spin S. Okay, why? Is because we are taking these two operator O for simplicity to be scalars. When you have a 2-point function of scalars, here you cannot have parallel spin. This is easy to show. In case you have spinning operators in the bulk, then you can also have parallel spin here. But this is the case we won't consider in this talk. So when you have scalars in the bulk, you just have to sum over delta hat and S. Okay, so the crossing equation now is the quality of these two expansions. Okay, sorry, yeah, I said it and I didn't put it. Thanks. So the crossing equation now is just this particular equation where you actually have that a 2-point function expanding in the bulk is equal to the 2-point function expanding on the defect. So you see, this is a very non-trivial equation, as all the crossing equations also in homogeneous CFT, because it's an infinitely many equation for infinitely many variables. But the nice thing about defects is that compared to homogeneous CFTs, where you have essentially the same set of defect CFT data on both sides of the crossing equation, where you have 3-point functions here and 3-point functions here, in this case, you're equating 3-point functions, bulk 3-point functions times 1-point functions in the bulk to square of bulk to defect couplings. Okay, so it's a very different setting where you're equating two different set of data, right? Which is also very powerful for us, because the idea is that this part of the information, the idea of the talk will be to use only this information here, only 3-point function and 1-point functions, to actually compute these couplings here. Okay, so the idea is that we're gonna use one channel to extract information about the other channel, and this is very powerful because, of course, 1-point functions are easier observable to compute in a CFT, in a defect CFT, and if I can use only these observables to extract the full correlator or to extract information about this bulk to defect couplings, this is very powerful. It tells you essentially that these bulk to defect couplings are somehow inherited from the 1-point function, so they're not independent. This is a nice feature. Okay, this crossing equation is a nice feature. It's also a drawback, because it's the main reason why people cannot straightforwardly apply the numerical bootstrap techniques to these correlators. Okay, because we have one of these two channels that is not positive. So if for the experts, or maybe you heard that the numerical bootstrap techniques, the success in solving the 3D easing model, is based on the fact that the crossing equation is a positive equation. Positive in the sense that when you have a square of P coefficients and you have a unitary theory, the square gives only positive numbers. These objects are real. The square is always a positive number, and then you can use semi-definite programming to actually constrain the allowed set of defects of CFT data, or But you cannot do it for defects because this channel here is a square, but this channel is not a square. So it may well be that one of these two objects, both these objects are real, but it may well be that one of these two is negative, and then you haven't got positivity. Okay, I'm spending a lot of time on this, but it was necessary. So now, how to use this crossing equation? Well, as I said, we cannot use it numerically. Let's try to use it to exploit it analytically. And the main idea of the analytic bootstrap is to look at the analytic structure, as I said, the analytic structure of this correlator, two-point function. Is a function of z and z bar. As I said, when you're in Euclidean, you have this configuration where z and z bar are complex conjugate of each other. But when you move to Lorentzian, this is not true anymore. Okay? And in particular, you can take this function f of z and z bar to be a function, a function of two independent complex variables. Okay? And this function of two independent complex variables will go to the Euclidean region or to the Lorentzian region, depending on which projection you make on these complex variables. Okay, so let me take first the Lorentzian picture. Lorentzian picture is very similar to the picture above. It's essentially again, you can go to a conformal frame where you have, where did I put my red chalk? Here. You have the defect in the origin. You have another operator in 1. But the difference now is that you are in Lorentzian, right? So both the defect and the operator, they have a light cone in these two orthogonal directions. And the z and z bar variables, of course, now this is not y anymore. This is x, this is time. Okay, so you have to analytically continue. This is super trivial, right? So you have now the z and z bar variables. They're two independent real variables. They're essentially light cone coordinates. And in my conventions, let me get this right. This is z equals 0. This is z bar equals 0. This is z equal 1. And this is z bar equal 1. Why is this important? Because these are light cones, okay? And so you expect that when you meet a light cone, so you start with some operator that is sitting here in z, z bar, some point z, z bar. Then you move around, okay? So here you have z and z bar are both in less than 1, greater than 0, between 0 and 1, okay? And then you move around. So this is called the Euclidean region, actually, because all the operators are spatially separated. And now you get closer to a light cone, and you expect that when you meet a light cone, you find a singularity, okay? And when you find which kind of singularity, well, you know from quantum field theory that the singularity that you find when you meet a light cone, they are branch cuts. And you need to pick a Feynman prescription to go above or below the branch cut. Okay, so you expect essentially that when z and z bar are real, they have branch cuts. In which positions? They have branch cuts at z equals 0 and z equal 1, and z bar equals 0 and z bar equal 1. So we expect essentially an analytic structure that is the following, both for z and z bar. Okay, so this is meant to be a function of two complex variables that both have the same analytic structure, with a branch cut starting in 0, branch cut starting in 1, and of course this branch cut end at infinity, where you have another branch point because of the defect that pinches the surface at infinity. So now the idea is that, of course, if you analytically continue where you actually move along some, so if you follow paths that are complex conjugate of each other, something like that, where you move z in this direction and z bar in this direction, then the function z of z bar should be single valued, because you're moving in some particular path in these two complex two complex variables that are complex conjugate to each other, which means that you're all the way Euclidean. Okay, you're Euclidean for the whole time. But if you don't do that, then you have a branch cut. Okay, so this is an additional constraint that you can put on your function. That, okay, I mean, whatever function you find for this correlator, it has to have these branch cuts, but it also needs to be such that when you move along a complex conjugated path, you find a single valued function. Okay. So now, what are these points, z to 0 and z to 1, or z bar to 0, z bar to 1? So it's important to actually understand what is in the crossing equation, what is the convergence radius of these OP expansion. So when is, what is the physical meaning of this expansion here? So this is an expansion where these objects have are powers in z and z bar, and plus the hypergeometric functions that resums the contributions of all the descendants. Essentially, the behavior of these guys is such that this series expansion here is convergent for z and z bar going to 1. How do we understand this geometrically? Well, it's very easy, because z bar to 1 is essentially what you want to do in this case. You want to bring the two bulk operator close to each other, right? So in this picture here, where the operator is at z bar, you essentially want to take this operator close to 1. And this is the limit where z and z bar, they both go to 1. The opposite limit, where z and z bar, they go to 0, corresponds to bringing the operator close to the defect. So this is actually convergent for z bar going to 0. This is important because now when you want to look at in Lorentzian, and you want to use this block expansion and understand the Lorentzian structure, the singularity structure, this singularity structure is reflected in the blocks. And to see the singularity for z and z bar going to 1, you actually need to use the bulk expansion. To see the singularity of z and z bar going to 0, you need to use the defect expansion. Okay? So now, I'll maybe, given time, well, it's not that bad. It's bad, but not that bad. Let me introduce two different variables for this z, for this cross ratio, so a different parametrization that is particularly convenient for defects. This parametrization is the following. So what is this? This is essentially complex. This is like, so if you're in Euclidean, this W is simply a phase, right? It's just a parametrization of a complex number. And if you are, this is the Euclidean. If you are in Lorentzian, then W is just a real number. So why is this convenient? Well, it's convenient because if you write your defect expansion in these variables, the blocks here are completely factorized. This is a super nice feature of defect that doesn't exist for homogeneous CFTs, is that essentially the blocks, this f tilde, this f hat, if you write them in these variables, they are completely factorized in a function of r times a function of w, and this is the reason why we can solve this explicitly. But that's not the only thing that we care about for this talk. The important feature of these variables is that you can now use an easy technique to actually work out a dispersion relation for the correlator. Okay, so how do I do this? Well, I simply look at the W function. So the complex plane of W, where do I expect branch cuts? Well, I expect to have branch cuts for W Well, you can look at the picture right there, and sorry, at the change of variables and the picture. And so you have z equals 0, z equal 1, and z equal infinity. So you would have branch points for w when w equal r, because when w equal r, z bar goes to 1. So let's pick, for instance, here r. You would have a branch point for w equal 1 over r. And then you would have w equals 0, where a funny thing happens, because w equals 0 is when z goes to 0, but z bar goes to infinity at the same time. So this is a bit of a bad branch point, and we will see why. And you have another one for w to infinity. Okay? So this point here is essentially associated to z bar to 1, and this point here is associated to z to 0, z to 1. So this is important, right? Because the points z bar to 1 and z to 1 are the one that they control these two branch cuts, whereas the points z equal, in this case, you have z to 0, but you have also z bar to infinity. So this is a point that is not controlled by an OP. Okay, this is not a point that we can access through an OP. And this is the main issue. So because the idea now is super simple, and this is if you look at the papers where they work out dispersion relation for CFT correlators, they're very complicated. There's a very nice paper by Carmi and Caron-Wu, because they have to deal with a double discontinuity. In this case, we can essentially use Cauchy theorem. So it's you have to determine a function of r and w, and you just say that this function of r and w is a contour integral of dw prime over 2 pi I of the function of r w prime over w prime minus w, where this contour integral is around the point, a generic point w prime, which you can take, for instance, here. Okay, and then what you do is you deform this contour and you map it to some other contour that goes around here and around here. So you can actually show that if you manipulate this contour and you rewrite it in this way, you can actually write this equation in a different way, where this integral now becomes the integral is not a contour integral anymore. It's just the integral on. You also have to use a symmetry actually that w goes to 1 over w, which is kind of explicit from the structure of the cuts, and is a true symmetry of the correlator. And now you have dw prime over 2 pi I 1 over w prime minus w. I write the full expression. It's not, well, just to show that it's particularly simple. It's a super simple kernel. So you have to integrate essentially whatever discontinuity you have in the function w as an integral. So you have an integral of this discontinuity across this cut and across this cut, okay, of the function. You integrate the discontinuity with this kernel and you get the full function. So this is similar to what people have done for scattering amplitudes back in the days for the S and T Mandelstam variables, and you do this on a single variable. Okay, this in principle you can also do it for CFT correlators, but it's not very useful. The reason why this is very useful for defects is because of what I was saying before, that these R and W, they are associated to the delta hat and S in the defect block expansion. This is particularly convenient in this case. And so the variable R goes for the ride. Okay, it doesn't play a role here. The only variable that you have to work with is the variable W, and this discontinuity is the discontinuity across the cut. Okay, so it's the discontinuity across this cut, which is, you see, the very convenient thing now. Okay, this is a dispersion relation. You can write it down essentially for any function that has that particular analytic structure. Now, how can this be useful? Well, the only way this can be useful is if I have a way to compute the discontinuity that is easier than computing the full function, right? As much as you do with unitarity methods for scattering amplitudes. Okay, you extract the discontinuity and then you can extract the full function. But this is useful if you have a way to compute the discontinuity that is easier than computing the full scattering amplitude. In this case, the same, right? I have to find a way to compute this discontinuity that is actually easier than computing the full correlator. And the reason why this happens is that essentially what you can do, since this discontinuity is at the point r equal w, so it's the discontinuity across this cut, so it is controlled, I can safely insert in that expression the bulk expansion. I could not insert the defect OP because the defect OP does not converge here. The defect OP converges in a point that is not a nice point in the W plane, because I need to send Z to 0 and Z bar to 0, which means R to 0. But the defect, the bulk OP, so this OP here, converges for Z bar to 1. So if I need to compute the discontinuity, I can actually insert this expansion and then compute the discontinuity of the bulk block. Okay, and this is easier because the bulk blocks, I know them. Again, this might not be that easy, even if I know the blocks, because there are infinitely many. So the idea is that W20, well, I should say, there's a subtlety, but it's super important subtlety, is that when I did these manipulations, I neglected contours, right? I neglected the contour at infinity, and I neglected the little contour here around W equals 0, which are mapped to each other into this W going to 1 over W subtlety. This means this is something that in principle I cannot do for any generic function. I need to assume the behavior, some particular behavior of the function f of Rw when W goes close to 0. And this is a limit that is not controlled by an OP. This is known also in homogeneous CFT. It happens. It's known as small spin ambiguities for this formula, and the idea is that essentially what happens here is that this region is controlled by operators that are exchanged in the defect OP that have small spin. I don't have really time to go into the details of this, but I can tell you more if you have questions later. But the idea is that the results that I get is right up to the small spin ambiguities that then I can fix, I hope to fix in some other way. And if I cannot do it, I'm screwed. Okay, then let's see now the important thing about these defect blocks, how they behave, right? So I know them, I told you I know them explicitly or more or less explicitly, but what I know always is that these defect blocks, f of delta L of R and W, now they are function of R and W, they always behave like W minus R to the delta minus L over 2 minus delta O, where delta O is the dimension of the exchanged operator, times F tilde of R W. And this F tilde, what is the property? This property is that this is regular for R going to W. So that means that the full the discontinuity is completely controlled by this prefactor here. So what could happen is that in general, of course, this is a nightmare anyway, because you're summing over delta and R. So if this is completely general, this delta is not integer. This is just a branch point for each operator. Okay, so infinitely many operators contribute to this discontinuity. So, but what simplifies things is when you have deformations of GFF. GFF being generalized free field theory. Generalized free field theory is essentially a theory where you have that the operators are, the correlators are computed by Wick contractions. And the important thing about the spectrum of GFF is that the spectrum of GFF is only made of operators that have integer scaling dimensions. And then you can have some perturbative parameters, whatever perturbative parameters that you want. And I'll give you examples where you have these perturbative parameters, and you have some corrections to this dimension that is an anomalous dimension. But the important thing is that, okay, you will have in GFF some spectrum of operators that are known, and these are the so-called double twist operators. So what are now the contributions? The contributions to these, so for double twist operators, the dimension is an integer. Okay, so what are the contributions to the discontinuity now? Well, you have two kinds of contributions, essentially. You have contributions from double twist operator at next to leading order, where their dimension becomes non-integer, and therefore you degenerate logarithms of these expressions. And then you have infinitely many double twist operators contributing to this discontinuity. Or you may have discontinuity that arises because essentially this object here, you can also have discontinuity because this becomes a pole. And a pole has a discontinuity that is a delta function. Okay, so delta when delta minus L is less than 2 delta O. So let me try to summarize. This discontinuity here encodes finitely many operators, right? Because delta O is a finite number. In our case, will be 2. So this includes only operator with twist less than 4. Okay, and it can be also infinitely many, but in our case, it will be finitely many. And then you may have this, but in cases. Yeah. I'll get into details. Well, it's also true for other cases. In all the cases I will mention in a second when I list the application, these will be finitely many operators. But of course, you also need a mechanism to suppress all these other operators. Okay, so to suppress all these contributions. And the mechanism in n = 4 superior Mills is holography, where double twist, double trace operators, they have an anomalous dimension that is suppressed by 1 over n squared. And therefore, these operators, they don't contribute to the discontinuity. So let me now list the applications. And then, well, I don't have time to go much into the details of surface operator, but maybe just mention what is the main result. So this has been applied, this dispersion relation, which I should mention actually, we worked out this dispersion relation with Davide Bonomi, and in a parallel paper it was worked out by Pedro Liendo, Julien Barrat, and Aleix Jimenez Grau. And this has been applied to different cases. In particular, Wilson lines in n = 4 superior Mills theory. It's been applied to surfaces in n = 2, 0 in 6D. Been applied to the ON model for a localized magnetic field. This is the work I've done with Davide and Elia De Sabata. Localized magnetic field in epsilon expansion for the ON model. And also for what is called spin impurity in the O3 model. I'm just listing some contributions here, again in epsilon expansion. Okay, so you can do it for supersymmetric theory, but you also have some mechanisms that in epsilon expansion simplify things. I can give you details if you want later, but in some more realistic theories like the ON model. And what the application that I wanted to discuss in this talk, but I now have very little time, is a surface defect in n = 4. So maybe I'll take, it's okay if I take 10 minutes, 5 minutes? We started a bit later, yeah, so, yeah.
Let's start with the work that you did, because Wasn't the dispersion relation known already, or is that?
No, no, no.
That's the
Yeah.
in this cartoon.
That, well, was known already. What do you mean? We worked it out, but some years ago.
Okay.
If you mean it was already known by
Yeah, but what's the work in progress now?
the work in progress is this, applying this to surface defects. Sorry, I didn't get to that. The dispersion relation was known, yes. We worked it out a few years ago. Now let me try to say, yeah.
Where the Euclidean picture was giving input. I mean, you said that you have branch cat, but it should be regular when Sept and Sept are conjugate.
Yeah, so essentially suppose I know this function of z and z bar.
Yeah.
So what you need to check is that essentially if you take analytic continuation of this function going to the branch cut, but going in complex conjugated path, it is single valued.
Yeah.
Okay.
This helps you to derive the dispersion relation, or
This doesn't help in deriving the dispersion relation.
what does it help to do?
Well, it's a consistency check if you want, because it's a consistency check when you find the result, right? If you find the result, you need to check that this is true, and the dispersion relation, as I said, is not the end of the story, because then you have these ambiguities, and then when you have to, and then it's more of an art. Yeah, for that it doesn't help. Because this W20 limit is really weird. It's really hard to it's really hard to control. It's not that you can. No, it doesn't help to know this.
So completely, you don't use this to solve or derive or solve the dispersion equations, but you use it as a further consistency.
Yeah, yeah, and effectively we never use it, and we always check it. But it's an additional constant because we can somehow solve the ambiguities, but it's not clear that you can always solve these ambiguities. And maybe I'll get to these low spin ambiguities, and then I'll say something more about this. But the idea here is that okay, what operators we look at in n equal 4 superior Mills are chiral primary operators. That so now a surface defect. Essentially is a defect that breaks the full superconformal PSU 2,2/4 down to PSU 1,1/2 squared, essentially, times U1. And the crucial thing, well, it's not really times, it's a central extension. There is a central extension of U1, and the crucial thing is that you expect to have two U1s there, because here you have, what do you have? You have let's look at the bosonic subalgebra. You have the conformal group, let's say in Euclidean, times R symmetry, SO6. And this is broken down to, well, let's call it as you prefer, as you can call it, SU1, 1 if you want, the square, that is the gauge, sorry, SO1, 1 squared, or SU1, 1 as you prefer. That is the conformal group in 2 dimensions, right? 2 copies of the conformal group in 1 dimension, and SU2 squared, which is just breaking down essentially. And then here you expect, because what you're doing, you're breaking down SO1, 5 down to SU1, 1, that is another name for SL2 squared, that is the conformal group in 2D, times, and then you expect to have a U1 that is orthogonal rotation. Let me denote it like this. And what you're doing is you're breaking SU4 times to SU2 squared times some U1 that I will denote by R. That this is the pattern of symmetry breaking. The crucial thing is that here you don't have 2 U1s, but you have just 1 U1s that is given by a combination of R symmetry and orthogonal rotation. Okay, so in general, defects in surface defects in n equal 4 superior Mills do not preserve orthogonal rotation and R symmetry separately, but just a combination of those. The other combination is an outer automorphism of the algebra, which means that it sends the algebra to itself, but it's not part of the algebra. So this can or cannot be preserved. Okay, is not. If this is preserved, it means that orthogonal rotation and R charge are separately preserved, are both preserves. Okay, but it can also be broken, and if it's broken, it means that just a combination of these two is preserved. Why is this useful? Well, the operators that we want to study, these are the so-called O2 operators that are essentially obtained by taking two scalars, the six scale quadratic form of the six scalars of n equal 4 projecting down to the symmetric traces. So this is a null complex vector. SO6 complex vector. So it's a vector of SO6, okay? Which projects these are six scalars in n equal 4 superior Mills that are projected to the symmetric traceless representation, and then you have that this function now will depend on x and on y. And then you have some additional complications in these 2-point functions that you have. Now you have a prefactor, which, okay, let me just denote it like this. Sorry, this is not true, actually. These are orthogonal products, essentially. But you see that the pattern of breaking is very, very similar. If I wrote down the right thing, it's very, very similar. So you essentially have the same kind of breaking where you break down to orthogonal and parallel products of these y's. Again, I can give more details if you want. And these operators are protected. And in this case, they have dimension 2. So you just work out the dimension, and they have to have 2 y's. So this has already 2 y's, and they have to have dimension 2. So this you probably want to have a 2 here. Okay. And then you have a function here. And this function, let me call curly f, is going to be a function of z, z bar, but also two R-symmetry cross ratios, alpha and alpha bar. And so you have a more complicated structure, and you have to work out the structure of the blocks and the super blocks, which means resumming not just the descendants, but also the super conformal descendants. And you have super conformal word identities. And this is the last thing that I want to say, is that you have super conformal word identities which reduce these. So you have a super conformal word identity that are essentially similar to what you have in n equal 4 superior Mills without the defects. So essentially they tell you that if you take a derivative with respect to z plus a derivative with respect to alpha, and then you set z equal alpha, this has to be 0. This is a consequence of superconformal symmetry, but what is important is that this object is really similar to the 4-point function in n equal 4, and then you can, without the defect, and then you can solve this superconformal word identity, and the solution, which I can give you details later if you're interested, but the idea is that the solution is encoded in two functions, an holomorphic function of z and alpha, and a function f of z and z bar. So alpha, they are R-symmetry cross ratios. So the idea is that you can essentially, there is a parallel between this y variable and this x variable. Okay, so the same way you build space-time cross ratios for these x. So this z and z bar you can write down explicitly in terms of x1 and x2. In the same way you can write down cross ratios in these y variables. In terms of so if you look at this, right, they are completely identical, these structures. It's just some different projection in real projections. of these groups, right? But the structure is exactly the same. So the idea is that these y variables, they are coordinates on this R symmetry space, okay? And if I did this in the lightcon in the projective lightcon for this part of the space, you will find that they have exactly the same form. I can write this down explicitly, but it will take me a little bit of work, so I skipped it. But the idea is that well, maybe later in the question time I can give you explicit expressions if you want. But they're analogous to the z and z bar. So essentially they are cross ratios that you can build out of these y variables that gives you invariance under this SU2 squared times U1. Okay, I can be more explicit. Let me just say that essentially what we did is what simplifies things in this case is that when you go to the holographic limit, so large n and strong coupling, all these double trace operators, they are suppressed by 1 over n squared. So there is one single operator which contributes to the discontinuity. And so if I give you the explicit result, and then I'll stop for this function f of z and z bar, well, it's actually, yeah, well, I can write down a function f of z and z bar is the final result for the 2-point function at next to leading order. So the leading order is just 1 minus z squared 1 minus z bar squared. And then the next leading order, just to show you what controls this 2-point function, is super simple. So I can even write it quickly at the blackboard. And it is controlled by a single CFT data, piece of defect CFT data. So this is the full result. The next to leading order result for this function f of z and z bar is controlled by the 3-point function of the O2 operator in the bulk. That is an object that is fixed, it doesn't renormalize, is 1 over n essentially. Is a number over n. And the 1-point function of the O2 operator that is known exactly through localization. So this computes the first 1 over n correction to the correlator. This is the leading order. The leading order is essentially, well, there is also this function here. This function here is controlled by a solvable subsector of the theory that is known as the chiral algebra. And this is also known, we computed it. But the important information is here in this function. The leading order is essentially, what is the leading order? The leading order is just big contractions of these two fields in holography. That is just the correlator without the defect, essentially. And the first correction to this, which would come from different Witten diagrams, that if you're interested, I can tell you which Witten diagrams how would you do this computation in holography later. I have prepared something on this. But the idea is that you have many Witten diagrams to compute, but in this approach, you have nothing to compute, because these objects are both known from localization. Well, this is known since the early days of ADS-50, and this is known from localization in a recent paper by Gomis et al. So this is the first subleading 1 over n corrections to the correlator completely computed by a single piece of defect CFT data. And this is the power of the dispersion relation, essentially, and holography. There are subtleties here that I haven't talked about, but I have no time to talk about. So if you're interested, you can ask about them. But I really should stop because I'm over time. Thank you. Yeah. Exactly. Well, good, depending on what you call a good module. But they are bad modules to me, but they are modules. So the idea is that essentially what you have is the following: that you have this O2 or maybe even better, you have the function f, the function curly f of z, z bar, alpha, alpha bar. And now if you take this and you take it at the limit where it becomes completely holomorphic, okay, so z bar equal alpha bar.
So this is the twist.
Exactly, exactly. This is precisely the twist. This becomes identical to this function f of z alpha. I can give you the, I mean, we have a full expression of this function f in terms of this function big F and this plus z alpha bar plus z bar alpha, and there are all the combinations that you can take different twists. Because here you are in n equal 4, so you can take different kind of twists, right? Because you have more, the chiral algebra is still supersymmetric. So now, what is the interpretation of this object in the chiral algebra? Okay, in the chiral algebra, essentially, what you're computing is this sigma, this is the module, at infinity, then these objects here, these O2 operators in n equal 4, well, you probably know they map to so when you go down to n equal 2, you will have the superprimary of the stress tensor multiplet, you will have a moment map, and the moment map is the component that goes to the chiral algebra, that makes it to the chiral algebra. So the moment map, when you go to chiral algebra, it corresponds to Katz-Moody current. So the stress tensor is the R-symmetric current that make it. So you see, what you are computing here is the superprimary, right? N equal 2, but n equal, yeah, it's still the R-symmetric current, right? Yeah. But this is, yeah, this, of course, this is another option. You can go and compute the full supersymmetric correlator, but this is even harder, because now we are computing just the correlator of the superprimary. We're not inserting here the full super conformal structure of the descendants. So it's not completely clear how would I compute. I mean, you have to work harder to compute the correlator of the super descendants of this O2. Okay, so if I focus on the superprimary, though, I can actually isolate some components that make it to the chiral algebra, which is reflected by the fact that this object is not 0, and these components are moment map if you look at n equal 2. Moment map of the flavor symmetry that is actually in reality R symmetry for n equal 4, because there is no flavor symmetry in n equal 4, right? So
there's both the SU2 flavor moment map, which gets mapped, but then there's also the highest.
So, but this SU2, so essentially you are thinking of, you're thinking of SU4R as SU2R times SU2F. No, so the only one that makes it is the moment map of this, essentially, when you break down to SU2, when you break down to n equal 2. You get it. I mean, it's true that you get it, but it's the only one that makes it to the chiral algebra. Because these two, as you say, they are part of the n equals 2 stress tensor.
Yeah,
and
the chiral algebra operator from this n equals 2 stress tensor multiple is the SU2R current, right?
Is the current, yeah. Very good, yeah. No, it's the R current, but the R current is not one of the operators. So you see, by picking different values of y's, I can select the superprimaries of the n equal 4 stress tensor multiplet, right? The n equal 4 stress tensor multiplet, the superprimaries, they are dimension 2 scalars. And the dimension 2 scalar in the stress tensor multiplet does not make it to the chiral algebra, right? So now, so these are Katz-Moody algebra, Katz-Moody currents, essentially, in
You're looking at the SU2F as a component of the
right. So this is an SU2F that is not really SU2F, right? It's just one part of SU2 4R, but we don't really need great. So this is the interpretation of this function f of z alpha, where alpha it's some addition, because these are SU2 currents, so they will have indices, and then you can also play the same game as I did before, getting rid of these indices, introducing an R-symmetry cross ratio also here, and this will give you some. So all I want to say here is that these can be constrained, right? Because these you can, of course, these are modules. So this OPE channel is not that easy because when you bring the current on the module, it creates an excitations of the vacuum. But this asymmetry channel is completely under control. It's just a symmetry of two different Kac-Moody currents, and it contains a single current. And then, so Z21 should give you precisely the 3-point function of two modules and a current that you know well from two-dimensional. So this can be used. Actually, we use it because what I didn't say is that when we did this computation and we got this result, there was an ambiguity which is related to this low spin. It is this low spin ambiguity that I was talking about before. And to fix this ambiguity, we use superconformal word identities, so to make the correlator supersymmetric. But this was not enough. We had to use some input from the chiral algebra to actually fix this. And so this function f is known, and the interpretation is chiral algebra is that. Exactly. But even, I mean, here we didn't really need to input anything about the specific chiral algebra of n equal 4. This could be done for any chiral algebra. It's just, you know, it's just a generic thing about two-dimensional currents.
So is there a holographic calculation using, like, say, the brain?
Yeah. So the probe brain, okay, there's no holographic calculation. There's holographic calculation of this object here. And this is a paper, rather old paper by Drucker, Gomis, and Matsuura, where they did the computation of the defect expectation value of the 1-point functions of chiral primary operators and stress tensor in 3 different ways, essentially, and also the expectation value with another Wilson line. Both with the gauge theory, so at weak coupling with the gauge theory, at strong coupling with the probe brain, and the strong coupling with bubbling geometries. So the funny thing here is that the strong coupling with the bubbling geometry at large n is exact. And this is this recent paper by Gomis and some other people that I don't remember. But it's quite stunning, because you compute something in supergravity, and then you compute it through localization, and you find perfect agreement at large n. So essentially, the result is that this object here is known at any it's known at any value of lambda at large n, which makes actually our result exact in lambda. It's a first order correction in 1/n, but it's exact in lambda, because we just used the 1/n perturbation theory. So the computation, how would you do this computation in holography? Well, the way to do this computation, similar computation have been done for the Wilson line. It's very hard. So so you have ADS5, you have a probe brain which ends on the defect in the boundary. So this is meant to be ADS5. The probe brain is stretching in the bulk of ADS5, and then you have 2 points on the boundary of ADS5, which you take to be Kaluza-Klein modes associated to this chiral primary operator O2. And now, leading order, you just have this, and then another contribution at leading order. This is the correlator without the defect. It's just a disconnected contribution, which is the one that gives you this term here. It's not easy to see from this expression, but these terms is just a rewriting of this disconnected contribution in terms of z as z bar. And then you have another contribution that is the product of 2 1-point functions. The product of 2 1-point functions, you don't see it here because it's hidden in the f, in the small f. And then, okay, these are contributions, these are leading order, and then you need to compute next to leading order. And then what you need to do to compute the next to leading order, you need to start building new Witten diagrams. In the probe brain description, you need to start building new Witten diagrams. And then This has been done, as I said, for Wilson lines. You have some contact diagrams. You have some exchange diagram, and you have some defect exchange diagram. So these three classes of diagrams, they're actually known. The result of the integrals are known. So for any dimension and codimension of the brain, the hard part here is taking the Dirac-Nambu-Goto, Dirac-Born-Nienfeld action in this case. The Nambu-Goto action was for the Wilson line because of fundamental strings, but now you have to take the Dirac-Born-Nienfeld action, expand it in fluctuations of the metric and the fluctuations of the brain, essentially, and work out all the effective Lagrangian and the vertices. Then you put everything together, things magically cancels, and they give you they should give you a very simple result. That's what happens for the Wilson line. Even for the Wilson line, the calculation is very subtle, and I have to say, if you look at, there is a paper by Jimenez Grau, which we hit our heads on for some time, and the contribution of this contact diagram is super subtle, and I think it's still an open problem to fix this through really expanding the Lagrangian without making any assumption on any bootstrap calculation. The way he did it, after these two contributions came out right, this didn't come out right, and then he fixed this vertex by bootstrap, essentially, by the only way that could be consistent with superconformal word identities. But it's a very tough computation, I would say, much harder.
Might also because this probably hasn't been done to do this in the bubbling.
This hasn't been done for sure. The 1-point function was done, but the bubbling case, well, you know much better than me, but I have no idea how to do this. It's probably some holographic renormalization argument where you have to expand in higher orders in the metric, I suppose. But
any final questions? If not, thank you very much.
thank you.